Okay, the total kinetic energy of all the particles is therefore n over 2, well, it's n times 1/2 mv squared, where v is VRMS. Now, VRMS is just the square root of the mean value of v squared. If we total up all the kinetic energies, we're totaling up all the 1/2 mv squareds, and it's the average of the 1/2 mv squareds that we want to use here. And so that the v squared that we're using here is not the average velocity squared, but the average of the squared velocities squared. Okay? The kinetic energy in the x, the y, and the z directions is the same, so that's each of those is going to be 1/3 of the total kinetic energy. And maybe I'll put a total here, TOT for total. Okay, so that when we express the average force, rather the average pressure is 2/3 total kinetic energy over V. And remember, that comes from the fact we got before. We have average pressure times volume equals 2 times the total kinetic energy. Okay, and then that was the expression we had for the particle in one direction. When we allow the particle to move in 3 dimensions, we got 2/3 kinetic energy. Then we divide that by the V, we get this expression. Okay, it's very consistent with the expressions we had before. We have average pressure is 2/3 total kinetic energy over V. What is average pressure? Well, PV equals nRT, so the average pressure is nRT over V, which could be capital NKT over V, since little n big R is the same as big N little k. And using that, we can write the average pressure as 2/3 of big N times we can write the average pressure as NKT over V. 2/3 the total kinetic energy over V. Total kinetic energy is big N times the kinetic energy of a single particle. So KE bar is the kinetic energy of a single particle. And now we can easily solve this for that kinetic energy, dividing both sides by N, multiplying both sides by V, multiplying by 3/2 to get rid of the 2/3, we find that the average kinetic energy of a particle is 3/2 kT. It's a very important result, and kind of an astounding result. It says the average kinetic energy of the particles in a gas is the same regardless of the mass of the particles. So we have massive particles, carbon dioxide molecules, say, in air, and very light particles, hydrogen molecules and helium atoms and so forth. They're moving at different speeds, but they all have the same kinetic energy. The less the mass, the more speed the particle needs to get the same kinetic energy. Okay, so next we get to the question of what happens if we increase the temperature of 1 mole of gas by delta T. What happens to the total kinetic energy? I'm going to begin to address that on the next clip.